Welcome to the fourth lecture in Module 8. As you've learned in the earlier lessons of this module, mitigation is mostly comprised of choosing cleaner fuels or using less of them. But there's another option at our disposal here: carbon capture and storage and carbon sequestration. During this lecture, we'll be introduced to the basics of this set of mitigation strategies, including the controversy that surrounds them and their potential to contribute meaningfully to solving the climate change problem. The first portion of this lecture is devoted to a brief introduction of the practices associated with carbon capture and storage, or CCS, and the role that it can play in climate change mitigation. Next, we'll move on to the two types of CCS, non-biological and biological, which we also refer to as carbon sequestration. In the first lecture of this module, we were introduced to the variety of strategies that can be used to help reduce the quantity of greenhouse gases in the atmosphere and mitigate climate change. Carbon capture and storage, or CCS, is one of these strategies, although it doesn't neatly fit into the supply side or the demand side categories that we've already explored. As you'll recall, carbon capture and storage removes carbon from fossil fuels either before or after they're combusted. There are two major types of CCS. The first type uses non-biological mechanisms to prevent the interaction of carbon dioxide with the atmosphere. This is orchestrated by humans, and while it's being seriously tested around the world, it remains one of the less common mitigation strategies. The second type of CCS is more commonly called carbon sequestration, and it refers to the capacity of some biological organisms to extract carbon dioxide from the atmosphere and use it to create cellular structures. In other words, plants capture carbon dioxide and store it, or sequester it, in their tissues. Carbon capture and storage is widely regarded as a mitigation strategy that has significant potential, but one that can't solve the climate problem single-handedly. It's one element of a portfolio of mitigative actions. So carbon capture and storage can serve as a bridge between our current fossil fuel-based system and a lower carbon future. Because of its applicability to current technologies and fossil fuel-based energy sources, carbon capture and storage can help us reduce the amount of greenhouse gases we're putting into the atmosphere while we search for and refine zero carbon technologies. While electricity in some parts of the world is produced through hydropower, coal still remains the dominant source of electricity in the world. This is actually an opportunity, though. Carbon capture and storage can be applied to electricity production facilities to reduce these emissions as we transition away from coal. The benefits in terms of GHG emission reductions, however, are partially offset because a plant employing carbon capture and storage consumes more energy, and so it would typically produce more GHG emissions than a plant without carbon capture and storage capabilities. Overall, emissions can be reduced by 80 to 90%. Those dramatic reductions are cost-effective only if a significant price has been attached to carbon. The phrase carbon capture and storage consists of a three-part process. First, we collect the carbon dioxide that's produced through industrial processes or fossil fuel combustion. Then we transport that CO2 from the source to a storage location. And finally, we seal up that storage capsule, if necessary, so the CO2 can't reach the atmosphere. CCS can be applied to large point sources of emissions, like major CO2-emitting industries, hydrogen-producing plants, and large power plants that use fossil fuels like coal to produce electricity. Transport of CO2 links the source of the gas to its storage facility. Technologies exist to transport carbon dioxide in solid, liquid, or gas form, but there are trade-offs associated with each of these. Massive amounts of energy, for instance, are required to transform CO2 gas into a solid. Transporting CO2 as a gas instead of a solid is more promising because CO2 is actually already being transported via pipeline, for instance, across parts of the US and Canada. These existing pipelines have been constructed to use carbon dioxide to enhance oil recovery by injecting it into oil wells and pushing out usable oil as a result. So we have experience with technologies that liquefy and transport gas as a result of the massive liquefied natural gas industry as well. So this is another option for transport. The most commonly discussed storage option for captured CO2 is in geological formations, such as exploited oil and gas reservoirs, coal beds that aren't really of commercial value, and deep saline aquifers into which the CO2 would dissolve. In no case is CO2 injected into vast, empty caverns, but instead it's actually stored in porous sediments or liquids. Another storage option is to inject CO2 deep into the ocean, where it would remain isolated from the atmosphere for centuries. Over millennia, the CO2 would eventually exchange with the atmosphere, and the end result would actually be the same as if the CO2 had been injected directly into the atmosphere. But the key difference here is the time scale over which that would occur. The near-term dangers associated with this storage strategy are mainly ecological. The ocean in the direct vicinity of the CO2 injection site would be acidified, causing potentially dramatic ecosystem changes. The figure that you see here illustrates the trend in ocean acidification that's occurred over time due to human industrial pollution. Many people fear that injecting CO2, even into the deep ocean, will exacerbate this problem and contribute to coral reef mortality and some pretty devastating ecosystem impacts. The final way to store carbon dioxide after it's been captured is through the transformation of the gas into stable solids, or mineral carbonates. In this case, CO2 is reacted with metal oxide-bearing materials, yielding carbonates. These materials isolate CO2 from the atmosphere for millennia. Unfortunately, this is a really energy-intensive process, so it's not yet commercially viable. A full CCS power plant with mineral carbonation would require 60 to 180% more energy than a typical plant without carbon capture and storage. Now that we're familiar with the basic elements of non-biological carbon capture and storage, let's hear what the experts have to say. Follow this link to view a short video that presents the need and potential for carbon capture and storage as a climate change mitigation strategy. Of all the CO2 storage options discussed here, geological storage appears to be the most promising. We already have the technology to capture CO2 from large industrial facilities, and in some cases, pipelines are already in place to transport and store CO2 in depleted oil and gas reservoirs. This will become cost-effective with a modest price placed on carbon. Ocean storage is less attractive because there's many possible risks to ocean flora and fauna. Mineral carbonation is the least developed CCS technology because it requires massive inputs of energy. As we discussed, there are quite a few controversies surrounding non-biological CCS. Some fear a sudden release of highly concentrated carbon dioxide from underground reservoirs, although there isn't too much evidence that this is likely. More certain are the ecological impacts associated with ocean storage. Finally, some people argue that employing CCS only allows us to continue using fossil fuels, which will inevitably run out. So carbon capture and storage is at best a bridge from a high carbon system to a low carbon one. At worst, it prevents us from developing truly low carbon technologies and creating real solutions to the climate change problem. Now let's move on to a way of removing carbon dioxide from the atmosphere that the planet does all on its own. Extracting carbon dioxide from the atmosphere and binding it in the living tissues of photosynthesizing organisms is called carbon sequestration. Less commonly, this is referred to as non-biological carbon capture and storage. There are two core strategies that can be used to enhance the amount of carbon that a piece of land sequesters. The first, afforestation, is planting trees on land that has never, or at least not in recent memory, had trees on it. As such, there's a net increase in the amount of carbon that is bound into that piece of land. The other strategy, reforestation, is to replace forests that were recently removed. We won't discuss them here, but other ways of enhancing the land's capacity to sequester carbon are the use of soil amendments and no-till agricultural practices. The greatest controversy that surrounds the use of forests as long-term carbon sinks is that they aren't permanent. A forest fire could, and often does, tear through the area, combust the living matter, and release the carbon dioxide bound in the plant tissues back into the atmosphere. Humans could use the wood for fuel or clear the land for agriculture or other activities. So a key problem with carbon sequestration as a mitigation strategy is one of permanence. Issues of land management are really important here as well. A particular portion of forest might be preserved in order to sequester carbon, but an adjacent portion of land could be deforested instead. This is especially damaging if that adjacent area is particularly ecologically sensitive or culturally significant. Finally, there's considerable uncertainty associated with this method of mitigation. Tree species absorb particular amounts of carbon given a particular climatic state. However, as we've seen, the climate is changing. This complicates the issue of calculating how much carbon will be taken up by a given area of trees in the future. Because of these controversies, some scientists would argue that the sequestration of carbon in forests isn't the most effective long-term mitigation strategy unless we get better at managing interconnected ecosystems and verifying the carbon stored in our forests. During this lecture, we've explored a set of mitigation strategies that doesn't neatly fit into our supply side and demand side categories. We've learned that carbon capture and storage is the process by which we keep carbon dioxide isolated from the atmosphere, either through biological or non-biological means, rather than producing less carbon dioxide in the first place. We've learned about various storage mechanisms, including the trapping of CO2 in geological formations, the deep ocean, and stable minerals. We've examined the difference between afforestation, planting trees on land that never had them before, and reforestation, replacing trees on land that was recently deforested. The readiness of non-biological carbon capture and storage technologies and the permanence of biological carbon sequestration continue to inhibit the potential of these mitigation strategies. With that said, it's believed that there's great potential here for CCS to serve as a bridge between our high carbon present and a low carbon future.